We're now going to be taking a look at a disk method question involving a vertical line that we're going to be rotating around. If it's a vertical line we're rotating around, it's going to be with respect to y. So everything in our formula needs to be in terms of y. Let's go ahead and read this question. It says, consider a region bounded by the curve of y equals e to the x plus 1 squared. So right off the bat, we have a problem. And the problem is that this equation right here is in terms of x, and it needs to be in terms of y because it's going to be rotated about the line x equals -1, which is vertical. So keep that in mind as we go through and solve this problem. Okay, the region is also going to be bounded by the line x equals -1, which happens to be our axis of rotation, and the line y equals e. Y equals e is actually going to be sort of the top part of our region. So what is the volume of this region when rotated about the line x equals -1? So as I've already said, this alludes to the fact that if we're rotating about a vertical line, x needs to be by itself in all of our equations. All right, and of course x equals -1, which is part of our region, is already by itself, so that's good. But this right here, we want to get this x by itself because it needs to be in terms of y. So the first thing we're going to do is take the natural log of both sides to cancel this e. Once we do that, we get natural log of y equals x plus 1 squared. We will now take the square root of both sides to cancel this squared out, and we get the square root of the natural log of y equals x plus 1, and the final step to get x by itself is to subtract 1 from both sides, making sure the -1 is on the outside of your square root. And so now we get x equals the square root of the natural log of y minus 1. And again, that's step 0, or your initial step. Get x by itself, and we do that because we were rotating it about a vertical line, x equals -1. So it has to be in terms of y. And also, it kind of goes back to your limits of integration, or basically the range of your region is going to be going from where these two lines equal each other all the way up to y equals e. So your limits of integration are going to be in terms of y as well. All right, so now we're going to do the next step, which is to draw the Cartesian plane. And again, these two steps are kind of go together. Once you draw the plane, then you sketch your curve. So here's your first curve. This is the curve of, let's do purple here. E to the x plus 1 squared is right here. Okay. Your other curve is going to be x equals -1. And you've got basically two, your top limit is going to be, or upper limit is going to be y equals e. Your bottom limit is going to be where these two curves cross, which is y equals 1. Now you could figure that out analytically if you just set e to the x plus 1 squared. Actually, once you get it in terms of y, if you just set square root of natural log of y minus 1, and I'll just put it down here, equal to -1, right? You're going to basically solve for that, and you'll get y equals 1, which is where these two curves cross. Okay, next we're going to draw the shape of the disk, and again we're rotating it about x equals -1. So you can see that your rotation is going to be going around this vertical line right here. And again, it's okay if your axis of rotation crosses one of your curves. In this case, x equals -1 is actually the axis of rotation as well. But anyway, we're going to be rotating this region around here. And so our disks this time are going to be going like this. All right, and again, this is disk method because our curve butts up against the actual axis of rotation. There's no gap. When there's a gap, we'll be doing washer method. All right, that's step 3. We're going to move to step 4 now, which is to the lines of intersection of the disk and the curve on the Cartesian plane. If we take this region and we rotate it about x equals -1, we are going to get a bunch of disks that look like this. This is our cross section of our disks, and this is actually our radiuses. Okay, and so if we rotate it all the way around, we're going to get a solid, which leads us to visualize and see what this is going to look like as an end result. All right, so unfortunately I wasn't able to get a 3D rendering of this graph, but we can visualize that when we rotate this region around x equals -1, which is going to be this line right here, we're going to end up with something that looks like a bowl. Okay, and here is our region right here. Each of these disks are going to go this way, and if you make all of these disks from y equals 1 to y equals e, they will make a bowl. We can zoom out here and kind of see why it looks like a bowl if we rotate it again around the line x equals -1. This leads us to the next step, which is determine the radius of the disk. This is very similar, as you can tell, rotating around a horizontal line. You'll see the correlation as we go on. If the region being bounded is right of the axis of rotation, it will be our region in terms of y minus the axis of rotation. So in this particular case, we again are rotating around this line x equals -1. We can see that the region we're rotating is to the right. So all we have to do is take the equation for this curve in terms of y and subtract our axis of rotation, and that will give us our radius. You can see why you would do the right minus the left. So let's go ahead and do that. So our right region, again, we already determined to be the natural log of y minus 1. We're going to be subtracting that. We're going to be subtracting our left curve, or line in this case, of -1. So since we're subtracting -1, and we want to put that in parentheses, so it's going to end up being square root of natural log of y minus 1 plus 1, and therefore our radius is just going to be the square root of the natural log of y. So what does that mean? For any given one of these radiuses of our disks, it's just going to be the square root of the natural log of y. So for example, let's look at y equals 2. If we plugged in 2 here, the length of this radius would be the square root of the natural log of 2. All right, so it looks like it'd be a little bit less than 1, basically. Now, something you might not have thought about is this curve right here. Why is it that it's the square root of natural log of y minus 1? When we got x by itself and we took the square root, we actually could have done plus or minus here. The reason why we chose plus is because it's to the right of x equals -1. If it was to the left, we would have chosen the negative square root of natural log of y. But at any rate, it's to the right of our axis of rotation, so that, again, that's why for our radius, we do that curve minus the axis of rotation. All right, now we're going to determine the limits of integration, which is the range of our disks. If you just go back and look at your sketch, again, you can see that it ranges, and let's use, I don't know, pink here. It ranges from y equals 1 to y equals e. Okay, so I will just write that right here. Okay, step 7 is to set up your integral. Now again, if it's ranging in terms of e, then everything needs to be in terms of e. And again, it's the same volume formula before. It's basically your range of all of your disks of pi r squared from a to b. So basically, if you take the area of all of these from 1 to e, it will give you the volume of this bowl right here that we drew. So we are going to be going from 1 to e. Again, you can just pull the pi out of your disk or your circle area formula, considering it won't matter. Just take the integral and multiply by pi at the end. Now it's going to be a radius squared. So again, fortunately, we'll just be squaring that square root, and it will become easy to integrate. So it leads us to step 8 to make the integrand easy to integrate. The square root and the square will cancel, and you'll just be integrating natural log of y from 1 to e, multiplying by pi at the end. Step 9 is determine the definite integral. If you remember, the antiderivative of natural log of x is x ln of x minus x. So the antiderivative of natural log of y is y natural log of y minus y. And again, you will have that pi. It's going to be hard for me to zoom in here. You will have that pi on the outside that you'll multiply your answer by. and we're going to be evaluating this from 1 to e. So we're going to plug in our upper limit first. We're going to be plugging e in for y, and then we'll be plugging in our lower limit 1 in for y. And that's going to look something like this. So it's going to be e natural log of e minus. When you plug in the lower limit, make sure to put that in brackets because you will have to distribute this minus. Natural log of e is equal to 1. So you get e times 1 minus e, and you can barely see it, but there is a pi that you want to keep outside of here. I might zoom in just so you can see it. So you get e minus e for your upper limit, and then minus. Now natural log of 1 is 0, so it's going to be 1 minus 1 on the inside of here. When you do e minus e for your upper, you get 0. And over here, you're going to get minus 0 minus 1. Let's do some simplification there. So it's going to be pi times 0 minus negative 1, which is going to be pi times 1, which is just going to be pi. So the volume of this bowl is actually just going to end up being pi. The volume of this bowl that we get when we rotate this by x equals negative 1 is actually just going to be equal to pi, which is pretty cool. I like this example a lot because it involves, getting x by itself, rotating about a vertical line. But if you notice, it's basically the same steps if it's in terms of x. It just, in this case, it happens to be in terms of y. And for your disk and for the radius of your disk, you always want to do the rightmost curve minus the leftmost curve. That's it for this example. If you have any other questions about it, let me know.